Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Paschen-Back effect. Let's begin. Two scientists, one Paschen, another one Back. What are the observations they found in Zeeman effect? Zeeman effect, what we see when the spectral lines are passes through external magnetic field. External magnetic field, in this case the external magnetic field is weak magnetic field. Weak magnetic field, weak in the sense we compare the magnetic field in between the external magnetic field and the intrinsic magnetic field or the internal magnetic field of atom. Question arises, is there any magnetic field in that of atom? Yes. Due to the orbital angular momentum and spin angular momentum of electron inside that of atom, there will be an intrinsic magnetic field inside that of magnet. In case of Zeeman effect, the intrinsic magnetic field inside that of magnet is stronger than that of external magnetic field. That means in comparison to that of intrinsic magnetic field, the external magnetic field is weak. What happened in case of Zeeman effect? Let we take that is the atom, and that one be the orbital angular momentum L, and that one be the spin angular momentum S. That one be the spin angular momentum S, and their resultant magnetic moment, resultant orbital angular moment, the total angular momentum is the J, the total orbital angular momentum. Means L precesses around J, S precesses around J, but when we apply some external magnetic field along that of J direction, we apply the external magnetic field along that J direction, external magnetic field B, which is weak magnetic field. As a result, that total angular momentum precesses around that of external magnetic field, that J precesses around that of B. Here the external magnetic field is weak in comparison to that of intrinsic magnetic field of that of atom. That is known as Zeeman effect. But when the external magnetic field is strong, when the external magnetic field is strong magnetic field, that means when we compare the magnetic field in between external and the intrinsic magnetic field of that of atom, the external magnetic field is much more stronger than that of internal magnetic field. That's why what happened, the internal magnetic field of that of atom collapsed. Means the coupling of L and S collapsed, and they are individually precesses around that of external magnetic field. Okay, that we can see here. If that is the external magnetic field B, that happen in case of strong magnetic field, strong magnetic field. When we apply the strong magnetic field B, what happened? The L orbital angular momentum precesses around B. L precesses around B, and again S, that the spin angular momentum S also precesses around B. Precesses around B. Okay. When the external magnetic field is strong, means the internal magnetic field of that of atom collapsed. Due to that, L and S individually precesses around that of external magnetic field. This happened in case of Paschen-Back effect. That type of effect is observed by two scientists, Paschen and Back, and that effect is known as Paschen-Back effect. And due to this, the splitting of that of spectral lines also change, means the shifting of energy levels occurred. Let we study it here. First we introduce what is Paschen-Back effect. That is Paschen-Back effect, that is the splitting of spectral lines, the splitting of spectral lines, or we can say at the energy levels in a strong external magnetic field. Strong external magnetic field is known as the Paschen-Back effect. Paschen-Back is known as Paschen-Back effect. Okay. And the precision of L and S around that of external magnetic field B is quantized, means they follow the space quantization rule, means its Z component Lz and its S component Sz are quantized. Okay. And due to that precision is known as Larmor precision, and the precision takes place with that of Larmor angular velocity. So according to that of Larmor theorem, L precesses around B and S precesses around B, and that precision, that angular velocities of these precision are given as the precision of L. The precision of L, that is omega L, that is given as the magnitude of mu L, that is magnetic moment, orbital magnetic moment, to that of orbital angular momentum L into B. Okay. Mu L by L is known as E by 2m, E by 2m into B. Again S also precesses around B, and the angular velocity of that of S, omega S, that is mu S divided by magnitude of S into B, that is 2E divided by 2m into B. Okay. And since the orientation is quantized, the component of Z of L and S are given as the Lz component here, Lz component, that is ml into H cross, that is orbital quantum number, and Sz is known as ms, spin quantum number ms into H cross. Now, due to the application of that of strong external magnetic field, the splitting of energy levels occur, and the energy splitting due to that of L, and the splitting of that of energy or the change in energy due to that of S. Let we say del EL, the energy shift due to that of L, that is omega L into its Z component Lz. So that will be EB divided by 2m ml H cross, that is del EL. Then the energy shift of S, del ES, that is omega S Sz, that is 2EB divided by 2m ms H cross, that is del ES. Okay. Now the sum of these two interaction energies is the mean energy shift, the total energy shift. Therefore, these are the interaction energy. These are the interaction energy. These are the interaction energy of that of L, and this is the interaction energy of that of S. Then the total energy, the total interaction energy, the sum of these two interaction energy is the mean energy shift. Therefore, the total energy shift, the total energy shift is given by the total energy shift delta A. Delta E is given as the sum of delta EL and delta ES. Adding these two, that is what we found, ml plus 2 ms as common of what, EB divided by 2m into H cross. Now we write the energy shift in terms of wave number. In terms of wave number, we write it as nu bar is equal to 1 by lambda is equal to del E divided by SC is equal to, that is ml plus 2 ms EB divided by 2 msc into H cross. That total term is known as L naught, that is ml plus 2 ms, that is L naught, where L naught is the Lorentz unit, where L naught value is EB divided by 2 msc H cross, which is known as the Lorentz unit, So what we see in that of Paschen-Back effect, we see it in that of Paschen-Back effect, the splitting of spectral lines in a strong external magnetic field is known as Paschen-Back effect. How the splitting occurs? Due to that application of strong magnetic field, we mathematically see what is the energy shift. Let taking an example, we illustrate that of Paschen-Back effect. So taking an example here, we take the example to illustrate that of Paschen-Back effect. Example, let you take the transition between D1 and D2 lines of that of sodium atom. The transition given as 2p half 3/2 to the transition 2s half, transition from this to that. Then we write it, we take the columns as terms L, S, then the number of strong field levels. Here just write a point here. What is the number of splittings? How the splitting takes place when we apply that of strong magnetic field, and due to that of interaction energy, what are the splittings? Each field level is split up into, look here ML stands for orbital quantum number. ML is the orbital quantum number, and the values are from the values of ML from minus L to plus L, and it has the allowed values are 2L plus 1 number of allowed values, and again in case of MS, that from minus S to plus S, and the allowed values are 2s plus 1 number of allowed values. Due to the combination of these two, one spectral line, how much number of spectral lines are formed from this one spectral line? Due to the application of external magnetic field, the strong external magnetic field, that means L leads to 12 plus 1 and S leads to 2s plus 1. Then the total number of splittings, write that each of the field level, so each of the field level is split into 2L plus 1 into 2s plus 1 magnetic levels plus 1 energy levels. Okay, so in that of example, we look at that of transitions, terms L, S, number of strong field levels, and the number of strong field levels, that is 12 plus 1 and 2s plus 1 number of strong field levels. Here ML, MS, and shift in level. What is that of ML plus 2 MS? That is the shift. So we take one by one. First 2p, the term is 2p. L is in the for P, L is S, P, that is 0 1, that is 1. Spin is half. In spectroscopic notation we write 2s plus 1, let that value be A, and J. Here 2s plus 1, this is the spectroscopic notation. spectroscopic notation. 2s plus 1 is 2, so S is half. Number of strong field levels, that is 12 plus 1 whole into 2s plus 1, that is 6 ml. The value of ml splitting is L, that is 0 1. One 0. ms for 1 it is plus half and minus half, half minus half. L is 1, then the allowed value will be 12 plus 1, that is 2L plus 1, that is 3, that is 1 0 and minus 1. Here again, that is half minus half with the spin. The shift for half it will be 2 0 for half, minus half 0, then 1 minus 1. Then for 2s L is 0, sp half. Number of strong field levels, that will be 2, ml is minus 1 0, that values are half minus half, half minus half, 0 minus 1, 1 minus 1. Okay. For ml is 6, now we take the transition, and here we use the selection rule. The selection rule, according to the selection rule, the allowed transitions are given as, and the selection rules del ml 0 plus minus 1 and del ms is equal to 0. Del ms is equal to 0. According to the selection rule, we take the allowed transitions. Now draw the allowed transitions. The allowed transitions, that is 2s. Then for p line, that is the 2p line, it has two parts. One is 2p half, one is 2p half, and another one is 2p 3 by 2, 2p 3 by 2. So s level splitted upon 2, one is 1, another one is minus 1. S level splitted as number of levels as 2, splitting as 2. 1 is plus half, sorry, plus 1. This is the minus 1, that is the splitting is 1, here minus 1. In that of column we treat as ml plus 2ms, that is ml plus 2ms. Here is the ml, here with the ms. For that of line, the ml will be 0, ms will be half, ml will be 0, ms will be half. Just take the values of ml and ms. For minus 1, that is 0, 0, half, 0, 0 minus half. Again, that line is splitted up into 6 levels, that splitted up one into 3 levels, that splitted up one 3 levels. So the splitting of this line are 3 levels, 1, 2, 3. That splitted up on 3 level. This is the 0 level, 1, 2, 3. The splitting will be splitting, okay. Here the ml plus 2s value minus 2, minus 1, 0, ml values minus 1, ms values minus half, ml value 0, minus half, 1, minus half. Then it will be 0, 1, 2, values are minus 1, half, 0, half, 1, half. Now the allowed transition is del ml 0 plus minus 1, del ms is 0. So the allowed transitions, this is the transition from 2p to 2s, 2p to 2s is the transition. So the allowed transitions are given as, one is this level as 0 to minus 1, 0 to minus 1, 1 to 0, that is 0 to minus 1, 0 to minus 1, okay. It follow the transition rule. Then 0 to plus 1, here this 0 to plus 1, 0 to plus 1, 0 to plus 1 means ml and ms obey that of transition rule. Then 0 to minus 1, this 0 to minus 1, then 2 to 1, 2 to 1, then 0 to minus 1, this 0 to minus 1 there, 1 to 1 2 1 1 2 1. Here is the 1 2 1. These two lines are same, 0 0, the shift is 0, so it will be 0 2 minus 1, then 0 2 0 2 1, 0 2 1, 0 2 1, 0 2 minus 1, 0 2 minus 1, again 0 2 1, 0 2 minus 1, line from 0 to minus 1. Zero two minus 1, again line from 0 to 0 2 minus 1, 0 to 1. 0 2 minus 1, 0 2 minus 1, here there will be no such line, 0 2 minus 1 line will be there, again a line from 0 to minus 1, here 0 to minus 1, 0 to minus 1. These are the allowed transitions. So from this, when we apply that of external strong magnetic field, this for pi line, 1 pi line and 2 sigma line are formed. These two are sigma lines, one is pi line. This is the pi sector, this is the sigma sections. Okay, this is all about the examples, the transitions 2p to 2s, the sodium D line, D1 and D2 lines. So with the help of this visual lecture, we understand what is Paschen-Back effect. And we take an example of that of Paschen-Back effect, how the allowed transitions are carried out. We are taking the example, see the selection rule, and then see the allowed transitions. So with this useful and informative notes, let me wind up this session. Thank you.